So samplers, we've invested a lot of time in sampling research. So most people are not interested in sampling as a research agenda, but they're really interested in how to use a different sampler. So this is very important to understand. For us, a sampler is a very simple state machine which gets asked over and over again how long and what should it do next. So basically we have different kinds of phases. We have the typical functional phase, means the timer is not called at all. Then we get detailed and simple warming phases, and this will get explained better later when we do the hands-on. And then we get a simulation, which means you send the instructions to the timer. So you could think of, we have implemented many of them. So for example, one of the simplest timers is you run always in functional. You never send anything to the CPU. And you can say, oh, this CPU is always running at an APC of 2. But you get all the functionality. Maybe you're only interested in running network tests, or you're only interested in running this test, and for your first experiments you want the speed that this kind of sampler gives you. Other kinds of samplers are like always on, which means we don't do sampling. There's a very simple sampler that always determines to go into simulation at each different chunk of time, which means it would be like very, very slow, but it would be equivalent to simple scalar or whatever other simulations. And we've also implemented smarts and SimPoint, which are two publicly available research papers. And we've also implemented our own time dynamic sampling, which I'm going to talk a little bit later. So if you're familiar with SimPoint is one of the best samplers available, but it's good for spec and for other kind of benchmarks, because it basically gets the application, it runs the whole application, and based on the basic blocks that you're touching, it does some sort of analysis and determines the different zones of the application. So basically you go to that zone, you simulate for a small amount of time, and then you add those numbers up using their own formula, and it gives you the result. In a full system simulator, you cannot have this kind of simulation for several reasons. First of all, because of timing feedback, which we'll explain later what that means. And second of all, because you don't want to. So I'm not going to talk a lot about this, because if you went to the CMP, you've already seen the presentation of the paper about.
This is multi-core.
This is multi-core, sorry. No, the next one is multi-core, which is what Mateo presented this morning. So one of the main problems of having multi-core is that SimNow emulates each of the cores sequentially. It may not do so, but eventually we have all the queues of all the cores, and the timing that SimNow has used to emulate each and one of these cores may not be the exact same time that the different models want once they start executing all these instructions. So we have to put some kind of magic here, which is in between, and that magic, which is the interleader, tries to make the instructions appear to the timers as if they were being executed by them. So it's the one that really, if one of the timers thinks it's executing faster, we try to give them instructions in a faster way. And we also try to account for the errors that this may bring. Because if you have a barrier and one of the timers has already finished all the instructions, you have to determine that there has been a problem there and try to make the interval quantum that SimNow uses to synchronize each of the cores smaller, so that you don't get any into problems with this. Yeah, this is more or less what I was explaining. Yeah, the other important thing that we have here is the timing feedback. Since we are a decoupled infrastructure, simulation infrastructure, the CPU cannot really tell the functional simulation at each specific moment how much an instruction took. So after a while, when the simulation phase is ended, we go there, we gather that information, and we have to send it back to SimNow. And that is very, very tricky to get right, because basically what you're saying is that whatever the CPU decided that has happened in this interval is going to be good for the next intervals. And doing that is good enough in most cases. It's like you get a sample and you determine that the next samples are going to be exactly the same, and so you can switch and go to functional and go very fast again until you reach another phase. Or you can try to put a time predictor and try to analyze this as a time series prediction problem. So we've experimented with this, and it's kind of good. We have an armor-based model, and so you can, if you notice that the CPI or the APC is changing in a regular fashion, you can account for that, and you can put time series prediction there, which that's that. Okay, this was the thing that I wasn't going to really talk about. So SimLab currently hasn't got a way of having more CPUs than their models have. So if you go and open a BSD and it has 16 cores, it has those 16 cores. So in one specific problem that we had internally at HP Labs in the Exascale Computing Lab, we had to simulate 1,000 cores for a specific paper. So we were forced with the problem of, okay, we have this infrastructure. How can we extract 1,000 cores of instruction streams and send them to our simulator? So we did a lot of things that Mathieu explained this morning, which he can explain later to you, or if you have more questions. But so this is good to know, because it means that if you really feel that COTSon could be useful for you, but it doesn't really cover one part, there may be ways around it, and we're open to suggestions on how to change interfaces and